Yeah, we're up here in the northern Sierra Nevada. We're at the University of California Blodgett Forest Research Station. We're in a mixed conifer forest up here about 4,000 feet. A beautiful place. Here we are in almost the end of winter, but a little snow around, but still just a gorgeous place to visit. It's got a real interesting history. Of course, the first history is the native people. The Nesson people lived here for thousands of years and still live here today. A Native American tribe that was displaced very early because the discovery of gold is down the road here, down here at Sutter's Fort. So the Nesson people were really taken out very early after the gold rush. After that, harvesting of timber became very common here. And a company owned this place for many years called the Michigan-California Timber Company. And in 1933, they actually donated the land to University of California. So Berkeley's owned this place since 1933, has done a lot of research on it over the years. When it was donated, it was heavily harvested in the 19-teens. So a very typical operation was that railroad logging came in. So railroads were brought up here. They were strings put throughout the forest and then trees cut. Old technology, steam donkeys and ways of removing trees. Huge trees, probably trees harvested here 7 feet in diameter, 6 feet in diameter, 220 feet tall. That first harvest is somewhat almost a terrible thing that happened because it didn't really have forestry principles. It was more about extracting wood. So there wasn't as much, thinking about what we're going to do down the road. How are we going to regenerate this forest? In the 19-teens, after the harvest happened, there were around 6 trees per acre left, and most of them were trees that had almost no economic value. Those 6 trees persisted, and a lot of shrubs grew. The shrubs grew up like crazy. Eventually, we actually had cattle operations here, and there was a dairy. A dairy was actually here, and the cattle ate the shrubs and actually made dairy milk for decades. Eventually, the trees started to get a little larger, a little larger, a little larger. They shade out the shrubs. And today, you look around this place and you got all these big giant trees. It feels like some people would say this is an old growth forest. It actually isn't at all. It was harvested severely in the 19-teens and regenerated by itself. And then today, we have it around us, gorgeous, but it came from a very different beginning. And that beginning was something that happened all over California. Heavy harvest in the early 1900s, all over the Sierra Nevada, particularly places that had relatively level ground that they could get to with trains and the technology at the time. After 33, Berkeley didn't do much here, kind of held on to the land. We had a caretaker, not much activity. Probably activity begins in the late 60s and 70s, and when we start to do research here in earnest. And ever since then, this place has been really a incredible place for research and demonstration of forest techniques, management, and other activities. Been going on ever since the 60s and to this day. So here is a piece of ponderosa pine, a stump, one of those trees that was cut in the early 1900s. With that, we were able then to go out with a chainsaw and take the tops off the stump, and then bring these back to the laboratory, sand them nice and carefully, and Brandon Collins actually dated these materials. And what we see here are these small lesions, almost like cuts in our own skin. So the fire just causes a small lesion in the tree, and then the tree tries to grow around that with new wood and kind of bury the lesion. But before it can completely bury itself, another fire comes along, another one comes along. Here's one that's kind of interesting, 1776. The birth of the United States of America. A fire happened here at Blodgett Forest. 1794, 1819, 1847. So we see all of these fires occurring from the late 1600s to the mid 1800s, and every 7 years or so. Just a common occurrence out here. And my predecessor at Berkeley, a fellow named Harold Biswell, a really interesting guy, he said fire was almost as important as water and soil to the vegetation in California. And I think when you see this type of stuff in your hand and let's look at how often fire occurred, Biswell was right. It was so common, it was so important in really shaping this forest for millennia, keeping it really resilient, keeping it resilient to climate changes and also changes in fire regimes. So taking that fire out had huge impacts, and we'll see that today.
Okay, so I wanted to talk about how the management of forests can really benefit from forest research. So here at Blodgett Forest Research Station, this is what we call a working forest. And so we manage for certain objectives. Our primary objective is research. We try to facilitate research as much as we can. It's also a working forest in terms of doing a timber harvest. We've done a timber harvest here at Blodgett almost every year for the past 50 years. And so we're constantly looking for ways to have the forest management facilitate research, and likewise we try to learn from the research so that we can improve forest management. So the example I wanted to show you right here was doing fuel treatment. So we're trying to reduce fire severity. So when the next wildfire occurs in this location, we obviously want it to be a low severity fire, because one of the reasons is we want to protect this building that's behind me. And by working with the researchers and doing prescribed fires to help with their research, we can learn how to safely conduct prescribed fires. And so here in this location where I'm standing, we've done a prescribed fire 2 times in the past 10 years. And even though it's really close to the building here, I actually burned within about 10 feet of that building. But because we understand how to conduct prescribed fire and how we can do it safely, we were actually pretty comfortable burning all the way to this building. So again, just an example of how management and science can work together to improve forest management overall. So here's an example of some vegetation that has been killed by a prescribed fire. We actually call this top killing because oftentimes a shrub like this will resprout after we top kill it with the fire. I think this one is actually fully killed. I don't see it sprouting. But the point here I wanted to make was that when we use prescribed fire, we can actually target it to kill certain trees or kill certain shrubs, but then save other ones. And the example here is that incense cedar seedling right there. That survived through the fire. Even though it's a small tree, it survived through that prescribed fire, and this one did not. And that's actually beneficial in terms of the objectives that we had in this case. So this is an incense cedar tree, and it might be as many as 300 years old. Even though it's not very much bigger than these 100-year-old trees that are next to us here, we can core this tree and actually count the rings, the annual growth rings, and see how old it is. And so we know this is a really old tree, maybe 300 years old or so. The distinguishing feature, obviously, with this tree is this big fire scar that we have, where the inside of the tree has been hollowed out by fire. And this is fire continuously occurring repeatedly over time, eating away at this cavity, making it progressively bigger and bigger. And that's kind of one of the really cool features and one of the reasons why we know that fire was very common in the mixed conifer forest of the Sierra Nevada, because we have this as direct evidence, and we can actually sample this and take a sample and visually see how often fire occurred. The evidence is right there on a sample that we can collect.
So we're in compartment 240 here at Blodgett Forest. Mixed conifer forest, just like we were before. But this is a little different when you see there's so many more trees here. This is an area that hasn't had a lot of active management in the last several decades. Maybe 400 trees per acre. That's a lot of trees. And we're in really heavy shade. We're not going to find a place in this forest condition where we can get a suntan. It's a lot of shade, a lot of canopy cover right here. Place has been logged just like it was in the other site, maybe about 1915. Trees came back in, established, and then we took fire out. Fire used to thin this forest, killed small trees. So you had this ability then of the forest to maintain a lower level of trees per acre, lower level of fuel. So take that fire out and then go ahead 100 years, we have a forest condition like this, which I would say is quite typical for a lot of mixed conifer forests all over California, because we've had harvest and we've had fire suppression in all those areas. So with that much canopy cover, we have about 75% of the canopy above us is green foliage. So if we look straight up, about 75% of the air around us and the sky is covered in green foliage. That's very dense forest for the Sierra Nevada. When we have that much canopy cover, that just means the amount of light we get on the forest floor, of course, can be very low. We need then to see species on the understory that have that accommodation of really low light levels. And here's one right here. These are white fir. It turns out white fir is one of the most shade tolerant species that we have in the mixed conifer. So when we have this much canopy, we would expect white fir, incense cedar to grow in the understory, and that's exactly what we see, because of just their ability to live here and make a small living by growing slowly. The other species like ponderosa pine really don't have a chance because they need much more light. So ponderosa pine we're not going to see, but the white fir we will. So we have conditions like this where we have 400 trees per acre, lots of fuel in the ground. 2000, we came up with a study to try to understand maybe some of the ways we could restore this forest. So the idea is of coming in here, using techniques to reduce the number of trees per acre, reduce the amount of fuel in the ground, and the Fire and Fire-Surrogate study began. The Fire and Fire-Surrogate study was funded by the Joint Fire Sciences Program, 11 different sites throughout the entire 48 states, the lower part of our country, 3 sites in California, 1 right here at Blodgett. So the idea was to try to do prescribed burning alone, mechanical restoration alone, do a mechanical restoration followed by a fire, and then compare that to an untreated area and look how those treatments would actually reduce fire hazard, increase maybe tree vigor, things of that nature. So this is a control stand. This is the stand that has had no treatment since 2000 and really begins kind of that transformation. So it's really important to look at this stand and just get a sense of what it looks like. So we go to the other sites that have the active treatments and you look, you go, wow, this place has really changed. But this is all, they looked all like this to begin with.
Okay, so we're in the control stand, and this will be sort of our reference point to compare the other stops. And what I want to do is go through the fuel strata at each of these stands. We're going to talk about the Duff, we're going to talk about the surface fuels and the ladder fuels, and then finally the canopy fuels. But let's start by looking here at the ground. We're going to dig in here. We have to dig down a bit. There's quite a bit of Duff here to look at, but we're trying to look at the mineral soil and then what the depth maybe of that Duff layer is, where the partially decomposed organic material is. And here we're probably looking at, I don't know, 2.5 inches of Duff, which over this entire stand is somewhere on the order of 40 or 50 tons per acre of Duff. That's a lot. And as you remember, Duff isn't a huge contributor to surface fire behavior until you get ventilation. When you get ventilation, that's when Duff can start really adding to your fire behavior. Now, moving up to the next strata is our surface fuels, right? That's our freshly deposited litter. That's our dead and down woody, and then even some of these smaller trees. There's not a whole lot of shrubs in this because of the canopy cover. But if we're looking at surface fuel loads, this is very typical of a lot of our Sierra and mixed conifer forests. Places that have not seen fire for many decades, probably over 100 years, at least in this case. And we have quite an accumulation of this down woody debris. And that's partly because there's nothing other than decomposition that's coming to take any of this debris out of the forest, or at least convert it into something that goes into the soil. So we have constant deposition from the trees up above, right? That's anything, you know, when a branch breaks or when needles fall off from the wind, we have constant deposition and only minimal decomposition. So that means over time, we're gonna constantly accumulate. So as we get up, we're gonna start then to look at the next strata, and we're gonna think about these smaller trees that are probably my height or even a little bit taller. That's our ladder fuel strata. That's the strata that's gonna connect the surface to the crowns of the dominant trees. And that strata is important for vectoring fire to what we call crown fire, right? So as you think about a fire moving along the surface here, there's plenty of potential for surface fire behavior here, and there's even greater potential for crown fire given the connectivity of the ladder fuels here. Okay, lastly, we want to talk about the crown strata. So we talked about the ladder fuels. On this particular site, we have quite a bit of connectivity that can allow a fire to transition from the surface into the crowns of the dominant trees. Now what we want to think about is how connected, how much biomass is up there that's burnable. And when I look up in this forest, I see quite a bit of the crowns interlocking. There's some breaks here and there, but in general, given the high canopy cover on this side and what I'm seeing, there's pretty good potential to sustain crown fire once it finally gets up into this forest. And that's one of the concerns that we wanted to address with this study, is how can we change that fire behavior? Not only just dealing with the surface fuels and the ladder fuels, but what does it do if you start knocking out some of those crown fuels and create some discontinuities in that layer? Okay, so lastly, let's think a little bit beyond just the fire potential on this site and think about just the overall health of this forest, or the resilience. So with that many trees per acre, 400 give or take, it's difficult, right? There's a lot of competition between trees. They're competing for a limited amount of water, a limited amount of nutrients. And one of the things that we've noticed in these forests that have been missing fire for so long is that we're starting to see more mortality, particularly related to droughts, which is quite concerning given some of the projections if you think about where our climate is headed. So another aspect that we sort of added into this study was to look at the vigor of individual trees as it relates to these treatments. And given that we're here in the control with no treatment, this is kind of our benchmark that we compared whether or not we actually changed vigor of the overstory trees. And right here, I'm looking at a pretty decent sized 20-inch, 22-inch white fir tree that's dead, recently dead, and presumably from some combination of water stress and perhaps an interaction with bark beetles. But that's one of the things that these types of stands where you have this many trees, you're gonna see a lot more of this as we're headed into the future, a lot more of these trees dying.
So I wanted to talk about the concept of what I call Pyro Silviculture. So pyro, that means fire. Silviculture means treating forests to meet certain objectives, whether that be for wildlife habitat or reducing fire hazard, whatever it is. So Pyro Silviculture means combining fire with achieving forest management objectives. One of the ideas with Pyro Silviculture is to try to find ways to actually increase our chances of conducting prescribed fire in the future. So the structure that we're standing in right here, it has a lot of challenges with it with respect to doing a prescribed fire. There's a lot of surface fuel on the ground, so these logs and sticks in front of me, that's what we call a high load of surface fuel. And then the canopy density is also very high. There's a lot of trees in the overstory and a lot of trees in what we call the midstory as well. And those conditions, that forest structure, we know we can do a controlled burn safely in that structure, but the conditions under which we can safely do that are pretty narrow. We call that the burn window. And so those burn windows don't occur very often in this type of structure. So if we take a Pyro Silviculture view at that issue, that challenge, what we would do is think about ways in which we can manage the forest to increase our odds of doing a prescribed fire in the future. So in this case, what comes to my mind is reducing the canopy density. And we can do that with a treatment, with heavy equipment, with chainsaws, reducing, perhaps taking out these smaller trees, some of the big trees as well, and that will help us to actually create a condition under which we can more feasibly conduct a prescribed fire in the future. So that's one of the ideas behind this concept of Pyro Silviculture.
So we're in a different treatment type here. So the first site we saw the control that hadn't been manipulated in about 20 plus years. Here we're in a mechanical unit. So what we did here is a restoration with machines. Going in, reducing density of the forest, also treating the fuel. So the sequence of treatment here, in 2001, there was a commercial harvest and also something called a mastication. So the commercial harvest could take a tree about maybe 10 inches diameter or larger. And if that tree was deemed not necessary or in excess, it was removed. The log was taken to the sawmill and you made lumber out of it. The top was left here. All the limbs and the top was left. And we also harvested some relatively large trees. So we see behind us that there's some pretty large sugar pines, Douglas fir. And here we came into the stand and the trees that were in excess in terms of the distribution of number of trees per acre, and generally they're the ones that are shade tolerant, the white fir and also the incense cedar. Those were taken more, and the pines were actually left to try to get more of a balance in the species after the harvest. Since we had more of the shade tolerant, we'll take more of those out and actually leave more of the shade intolerant, including the oaks afterwards. After that was all done, there were still a bunch of trees here that were small, but they had no commercial value to a sawmill. Then a masticator came in here. A masticator basically will just shred the trees in place. It's got this big excavator arm, just like you would just to dig a trench and build a building or put in a pipe. But instead of having that bucket on the end, you take it off and you put a disc on there. And the disc has got teeth on the bottom and a little teeth on the edge. Spins maybe 500 RPM. And the disc will come down, the operator will take the masticator arm, go up to the trees that are below 10 inches or 8 inches diameter, and shreds them right in place. Crazy thing will go, and things goes, and the tree is just gone. Okay, just shreds it all up. After that was all done, there was material almost up to my knees. It was like 18 inches tall. And when you walked through here, you were constantly trying to walk, you'd fall over. It was so much material here. So in some ways, that's an interesting contrast. You're taking materials, trees that are live, standing, you've then shredded the wood, and then you put it on the ground. And then there's kind of a contrast there of what did that do to fire behavior? Adding surface fuel, but removing ladder fuel. This site also made money. So it actually did generate some revenue. We'll hear more about that a little bit later. So this site, since we took logs to the sawmill, generated a relatively high amount of funds. So after the treatment was done, we had the masticator come in and material was already then shredded. We were worried that layer of fuel would stay for maybe a decade or two. And if you add that kind of material to the bottom, you can really increase fire hazards. We'll be able to look at a place up here in a moment where we can have repeat photography, and let's look how that place has changed over time.
Okay, so we're at the mechanical only site. If you think of it, remember the sequence of treatments here. We had an initial harvest that was commercial harvest, separating out tree crowns. We had mastication to take care of the ladder fuels. And then we, over time, had some significant decomposition. But in the interim, there was quite a bit of tree regeneration, which warranted another mastication, which was in 2017. And that was really due to the tree regeneration starting to grow up into that ladder fuel strata. So for a moment, let's start thinking about the strata, and let's start at the bottom here like we did before at the control stand. And remember, keeping in mind the control stand that we started with, right? The deep Duff layer, the high surface fuel loads, the high conductivity with regard to ladder fuels, and we're gonna contrast that here. So come and look at this, mechanical only, right? We're gonna look at the Duff, okay? And remember, keeping in mind that our reference point is that control stand where we had about two or so inches of Duff. Here, we're looking at maybe something more on the order of, I don't know, 1.5 inches or something. So there's still quite a bit of Duff, and remember, this is mechanical only, so there's not a whole lot of removal of the Duff, right? There's no fire. We're really just looking at decomposition, maybe a little bit more decomposition since the stand got opened up, but still quite a bit of Duff on this site. As we look to the surface fuels, you can see around us, I mean, there's no shortage of surface fuels. There's lots of small branches. There are needles right around me. But in general, I would say that the surface fuels, and I think the data back it up, in general, the surface fuels are not nearly as high as they are in the control stand. And part of that is just that we've taken out the input for those surface fuels, right? If you have lower canopy up above, there's less potential for deposition. Plus, by opening up the canopy, you've sped up decomposition quite a bit. So moving up, right? We talked about our Duff. We talked about our surface fuels. We're kind of, I don't know, overall maybe in that moderate to low surface fuel in terms of overall amount in this stand. But let's think about the ladder fuel strata and try to put in your mind the picture of the control stand. And we're talking about almost two different worlds here, right? There's almost zero ladder fuels in this stand, right? There is nothing that connects the surface fuel layer to the upper canopy layer. And that's intentional, right? That's part of the mechanical treatment. That was the mastication originally, and then the second mastication, which took care of that regeneration. So this stand in its state right now is quite resilient to fire, despite still having a decent amount of surface fuels. Okay, as with before, we're gonna talk about more than just the fire hazard, right? So let's move into the forest health aspect of this treatment. And if you recall, back at the control stand, we talked about forest health probably being in that fairly low range, right? Just given all the competition among the trees. Here, because of the thinning of all the trees here, competition has gone way down. And as a result, tree vigor has gone way up. How do we know that? Okay, partly it's just experience and seeing the growth of these trees. But we also know because we took cores of each of these trees. We actually put hollow drill bit where we took out a core that has the series of tree ring widths in it. And in that series, we showed a pretty marked change in the growth rates patterns after the harvest, the initial harvest. And that growth rate change is correlated to increased tree vigor. So not only have we mitigated the fire hazard on this stand, but we've also improved the vigor of these trees on this site, which means that they're able to sustain drought. Like for example, the big drought we had 2012 through 16. We saw very little mortality in this stand following that drought. And that's because these trees had quite a bit of access to water and nutrients as a result of the thinning. Okay, now let's talk about forest carbon. Why do we care about forest carbon? We're increasingly, especially in this state, looking to our trees to be able to pull some of the carbon dioxide out of the air and sequester it in wood. So what does this stand mean in terms of carbon? And let's, as we've done before, go back and contrast to the control stand. The control stand, remember, about 400, maybe even more trees per acre. Lots and lots of forest carbon. The highest amount of carbon by far of any of the sites that you'll see today. But there's a contrast here. That's a lot of carbon, but it's not carbon that's very stable, right? Meaning that it's vulnerable. Now, think about the carbon on this site. Not nearly as much carbon, but we have to think about other things too. We took commercial products off this site. We took trees off this site, turned them into lumber, and they're sitting in, let's say, somebody's home right now. And that's technically being sequestered. So that's carbon being pulled out of the atmosphere and sequestered in a home, plus the standing carbon that we see on this site. So overall, we're sitting on a lower level of carbon relative to the control here, but it's a carbon source that's more stable because it's not as vulnerable to drought, not as vulnerable to fire, and we've created sequestration in commercial products. So overall, this site is a pretty good win with regard to forest carbon.
So here we're in a mechanical plot that we've actually had repeat photography. Pictures from the very beginning all through the sequence. Over to the right, we can see a sweeping white fir tree that's in the photograph. You can see the sweeping nature of its bole. And over here, we got a black oak that's actually leaning in with a little V. And both of those are in the pictures. And the pictures are quite remarkable when you see how dense it was the first time. There were trees everywhere. You can't even see back maybe about 15, 20 feet. And then we did that mechanical restoration with the thinning and also the mastication. And then we see it opened up. We see that surface fuel layer, it accumulated. By the 2009, about 80% of that surface fuel had decomposed. That was one of the most surprising things we found in the study of all. We thought it would take much longer for those materials to decompose. But by 2009, the surface fuels had decomposed so much that we actually had a very, very good fire hazard in terms of real reduction in fire hazard. We did a lot of other things here too, like soil assessment. We did soil compaction, soil fertility. These treatments had no detrimental impact to soil compaction or soil fertility at all. So a lot of different aspects of the treatments were quite powerful in terms of being very positive. Sometimes people say, if you try to do a restoration treatment with machines, chainsaws, it's a timber grab. That's nonsense. If you look around here, this is actually good. You know, look at this place. It's got a restoration idea, big trees, heterogeneity, ability to reduce fire hazard. You can do restoration with machines and you can actually make a good deal.
So a major consideration when we're thinking about these different fuel treatments and management alternatives, especially for the land manager, is kind of the economics of it and how feasible a treatment like this is on the landscape. So this particular treatment, it definitely has a cost associated with it, with that mastication treatment, but it's also a significant revenue generator. So the two commercial harvests that we've had out here, those harvests, they generate revenue that's then used to pay for the mastication treatments, road maintenance, the planning of the project. So that revenue is really important. And you can see from some of these stumps that we're taking out sizable trees. And this is something that's going to get sent to the mill and we're actually going to get a profit on. So, and then in terms of the feasibility of this, you know, as a land manager, I really love this treatment. It means that I'm getting a little bit of revenue and I'm able to reinvest that in the forest and do some of these more costly treatments. And this is a treatment that's really applicable over a large swath of land in the Sierras. We're certainly restricted based on, you know, steeper areas, inaccessible areas, but there are a lot of landscapes in the Sierras that this type of treatment would be applicable to.
So in the very first stop where we were earlier, I talked about Pyro Silviculture, and that was a very dense forest structure where it was going to be pretty hard to do a prescribed fire because of that structure. Now what we've done here in terms of Pyro Silviculture is we've prepared this structure I think relatively well to do a controlled burn or a prescribed fire. And that's because we've lowered the canopy density quite a bit, and we've also reduced the what I call the ladder fuels, or the mid-story layer of trees. And that's allowing the sun to really penetrate to the forest floor to dry out the fuel. So what that does is really broaden out the conditions under which we can do a safe prescribed fire. So in this stand, we have a nice big ponderosa pine tree right here. And the reason, as a Pyro Silviculturalist, the reason why I like ponderosa pine is because it has these really long pine needles, which when these are on the forest floor, they have a really good tendency to burn. So this is a really nice fuel bed to be able to burn. It's nice and light and fluffy, low density, and that makes for a really nice material. And so this is good that we have this ponderosa pine. If we don't use prescribed fire here, we're probably not going to get very much ponderosa pine regeneration, so we're not going to be able to replace this tree. And if you look down here beside me, none of these are ponderosa pine. You can walk around here all day and not find any ponderosa pine seedlings, even though there are potential parent trees. Now, if we were to, and that's really because we have not had fire here. Ponderosa pine is very much a fire-dependent species. So from a Pyro Silviculture angle, when I'm thinking long-term, if I want to incorporate fire in here, I actually want to regenerate ponderosa pine. So I could certainly plant if I wanted to, and that'd be a way to do that, but I could also use prescribed fire because I've set up this stand so nicely to use it, and then I would expect, after I did use fire, I would expect to get more ponderosa pine regeneration.
So we're in the mechanical plus fire treatment here. So it's the same mechanical treatment we saw before, where we did the commercial thinning, sent some of the logs to the sawmill to make lumber, and then the trees that blow about 10 inches diameter were left. The masticator came in and ground them up in place just like they did. But after that, we did a prescribed fire. The goal was to actually reduce that material quickly, right? So we can burn that material that's on the ground, and we use a backing fire. The backing fire is start the fire on top of the road and allow the fire to move slowly downhill. So it moves very slowly, has the shortest flame lengths of any prescribed fire, because here we already done the harvest and the trees that were left, we wanted to survive. We didn't want to kill many of them because the machines had already taken out the excess and the prescribed fire to come through with low intensity. It turned out it worked really well in terms of reducing that fuel load, because afterwards we had a very, very open stand, very little fuel, and then when we modeled fire behavior, even under extreme conditions, we'd have very little impact from a wildfire here. This would be a very resilient stand to wildfire. One thing that surprised us is, and you'll see in the photos, is we had this incredible shrub response. All of a sudden there were shrubs that were short, maybe a foot or two, maybe about 3 or 4 feet tall, and then at the end of maybe 10, 12 years later, they were 5 feet tall. And that was coming from the seed in the soil. So the soil basically sprouted and the seedlings began to grow, and they grew and grew and grew. And we had this incredible shrub understory. So after that shrub response, they grew up and there was so much shrubs, they're almost homogeneous conditions. We decided to bring the masticator in for a second time, bring down those shrubs again, grind them with that machine, create some patchiness to it, and then burn afterwards. We did that all in 1 year. So we did the shrub response with the masticator, and then we reburned. Turns out if we would have left a little time between those activities, we get some decomposition, especially the first time we burned this in 2001. We went from mastication, having that big old layer of fuel in the ground, and then we burned it in that fall. If we'd waited maybe a year or two, some of that material would have decomposed, some of it get compacted by the snow, and we would have less intensity. After the second fire is what we see here. So in 2018, we came back in here, we did the second fire, and what we see around us is really the culmination of 2 treatments. One thing I would say about this particular treatment, it's been a little bit more tricky to implement. We've had higher scorch heights, a little higher mortality, and it's been, from an operational standpoint, been a little more challenging, I think, for us to actually implement in reaching our goals.
Okay, now let's talk about our fuel strata. Remember our benchmark here. We're comparing everything against the control that had deep Duff Layer, lots of surface fuels, lots of connectivity among the surface fuels, lots of ladder fuels, and pretty dense crown fuels. So we're going to contrast that with what we see here in the mechanical plus fire unit. So let's start at the ground as we have before. Okay, so let's start looking at that Duff Layer. Now, the interesting thing here is I don't see a lot of Duff. Where is it? I'm already at soil right now. That's soil. I mean, it's a little bit of charred soil, but where's the Duff? Well, it's gone because this has been burned twice. 2 times we burned this off, had really high consumption in this unit, and as a result, we're not sitting on a lot of material, at least right at the Duff layer. Now, moving above the Duff layer, we do have some surface fuels here. A lot of this is deposition following the last prescribed fire. So we're looking at maybe, what is it now, almost 2.5 years of deposition of these needles. But even at that, it's still not that thick. These are, this is not high hazard fuels. And if you look around just at the woody component of the surface fuels, it's just not there, right? You see a big log every once in a while here and there, but from a continuity standpoint, we're nowhere near what we were at in the control unit. So the ladder fuel layer, right? We started with the Duff, went to the surface fuels, and now we're on the ladder fuel layer. It's gone. There is 0 ladder fuel layer in this. And that's a result of the mechanical treatment, removing ladder fuels, remember, by mastication, but then the follow-up fires, right? We have 2 fires in this stand, which have effectively knocked out the ladder fuels, meaning there's absolutely no way you're gonna get fire to transition from the surface fuels into the crowns of these big trees here. And even if you look all the way up, so we go up to the canopy layer here, 0 continuity, right? There are no tree crowns touching other tree crowns, or if there are, maybe it's an isolated pocket of a couple trees, but 0 way to sustain a crown fire if you even got torching in this stand. Very low overall fire hazard here. Okay, as we've done at the previous sites, we're gonna talk about beyond fire hazard, right? And that really has to do with forest health. So how are the trees doing on this site relative to the others? Well, the answer, which is kind of surprising, is not that well. And it goes all the way back to the implementation of the original treatment, right? The idea that we created all those surface fuels that we call activity fuels from the mastication and from the harvest. Those fuels, given that the depth that we had in combination with the backing fire, allowed fire to sit on these trees for quite a long time. It could have been 10 minutes that these trees were bathed in fire, albeit low intensity fire, but that's a long time for these trees to be heating. And as a result, we actually injured the trees quite a bit. And that injury showed up in the tree rings. We could actually see it when we looked at the sequence of tree rings, that the vigor had dropped, the tree rings got narrower. These trees were not very happy. We didn't kill a lot of them outright, but we actually injured them to a point where they were having a hard time growing. And that has sustained itself to where we are now. We still are not seeing very, very healthy trees here. And that's something we can do, we can learn from and improve in future implementations of this treatment. What we can do is wait. As Scott said, we can wait in between mastication and burning. We can let some of the decomposition happen. We can let snow compact some of these fuels, and we'll get hopefully better results when it comes to fire. Now, what that means with regard to the vigor of these trees and their ability to respond or withstand drought means that these are not probably the best specimens of resilience. We don't expect them to do terribly well given another drought, but we can improve upon that, as we said.
All right, so this is another treatment that involved a revenue generating component. In the initial treatment, there was a commercial harvest in this stand, and that was a pretty significant commercial harvest to reduce the density of our trees out here. And it brought in enough income that we were able to, again, reinvest those funds into the future treatment. So the mastication and the burning were all covered by that first commercial harvest. And while there wasn't a commercial harvest as a component of the second treatment out here, the funds from that first revenue generating commercial harvest probably is still enough to cover at least a portion of the cost for that follow-up treatment as well. And this is certainly a treatment type where, as the land manager, I know that I'm sacrificing a little bit of growth on my trees here. So down the road, I might not have the potential to do commercial harvests like we did in the mechanical treatment. But that's okay. It's just a kind of a structure that we're accepting as a part of our general mix here at Blodgett.
So a lot of Pyro Silviculture is really managing fire for specific objectives. And what I thought I would talk about real quick here is managing for timber. And so when we use prescribed fire, in many ways, we're actually protecting our timber asset because we're protecting that timber from catastrophic loss from wildfire. But one thing about fire is that's really important to understand is it's a blunt tool. We can't control it. with really high precision. Certainly we can control it in terms of doing a safe and effective fire, and we usually can meet our objectives. But at the end of the day, you know, fire is this thing that we can't control with really high precision. So what I want to show you here is this stump that's next to me. We did a prescribed fire in this stand, and it was a pretty hot fire. We were kind of on the, you know, on the drier and hotter end of the conditions under which we prefer to burn, and we killed this tree with that fire. And so in this case, because we have a timber objective, we came back and we salvage logged this tree. So we were able to recover some value from it. Now we like snags, and so a standing dead tree is called a snag, and we like those because they're super important in terms of wildlife habitat. But in this case, we're trying to balance having that good wildlife habitat and also being able to sustain financially these treatments that we want to do. And part of that involves a timber operation. And so we came in and we cut this tree down and we sent it to the sawmill. We sold it to the sawmill to get some revenue back. And so that's just kind of the idea of Pyro Silviculture and trying to meet different objectives with prescribed fire. So I'm going to continue to talk about Pyro Silviculture. And where I am right now is a stand where we actually use prescribed fire as the very first fuel treatment that we did. We actually did not prepare it ahead of time. And that's something that you can do. We know from years of fire science research that we can burn lots of different forest structures given the right conditions. The issue and the challenge that we have currently is that those conditions for burning really dense forests are hard to come by. We actually need to have it be pretty dry in terms of burning in those types of conditions. In this case, we did it. We did a prescribed burn under dry conditions, and that allowed us to do more burns. We've actually done 3 burns over about the past 20 years in this particular case. And getting that first burn in was really key. If we can't get a first burn in because of constraints, permitting constraints, air quality constraints, something like that, we can do those other treatments ahead of time, like I've already talked about, manipulating the structure, doing harvests, doing mastication, stuff like that. So if we can pull it off, if we can do a prescribed burn maybe at the nighttime during the summertime or in the early fall, that's great if we can actually do it. But if not, then we start to think of these other ways in which we can lay the groundwork for later doing more prescribed burns.
So we're in the prescribed fire only unit, which is only using fire for restoration, 2002, 2009, and 2017. And this big old sugar pine in this picture is right over here to our side. So that first fire was quite interesting. We actually burned at night. We had high canopy cover. Remember that control, probably 75% canopy cover, at least 30 tons per acre of dead and down woody fuel on the ground that we see here, and also 30 tons of the material on the soil. We call that the duff. So we really needed dry conditions. So we burned at night, active ignition probably about 4 p.m. until about 10 a.m. through the night cycle. And that actually worked very well. It was amazing how well it worked. We actually were able to kill about 80% of the trees that were 10 inches diameter and achieve our objectives in reducing surface fuel and also forest density. After that, we saw some of the trees in the picture. They're standing dead, but they're still standing. And then after a few years, they rot and a little bit of snow comes, they come on the ground. Then we did the second fire. That second fire consumed some of those dead and down materials, also some of the shrubs that actually had regenerated, and further opened that stand. A lot of times we call that first burn a reclamation burn. You're kind of reclaiming the site for fire. The second one starts to get more of a mosaic, a pattern. You don't have quite as much continuity of the burning. And then the third fire was interesting too. When we tried to do both the second and third fire at night, we were unsuccessful. We actually had to go to the day because we just had different conditions, and nighttime we just had too high a moisture content, not enough fuel in the ground because of the first fire, and we had to have actually warmer conditions. And by the third fire, it's quite amazing that the most patchy fire of all. Some places completely unburned, other places burned. The first fire, since it had more continuity of fuel, much more homogeneous burning conditions. And in the mechanical plus fire unit, we use a backing fire. Remember, the backing fire comes down the slope. Here we use strip head fires. Here we set strips down slope and burn into areas previously burned, and maybe those strips are 40 feet apart. We wanted higher flame length to kill these trees, so it had a different firing pattern. But at the end of the day, it worked pretty well.
Okay, let's go through our fuel strata and remember our benchmark again, the control stand. So we're going to go through the duff layer, the litter layer, the surface fuels, and the ladder fuels. Let's go take a look at the duff. So as we dig down, it doesn't take long to get to mineral soil. which tells me there's not a lot of duff here. And as we look at it, I mean, we're talking about something maybe less than a 1/4 inch or something of duff. And that's really a product of the 3 prescribed fires on this site. As we move up to the next layer, the surface fuel load layer, we're looking at a lot of litter, at least locally here, ponderosa pine litter here. But then from a woody component on the surface fuels, there's some, but there's nothing close to what we saw in the control stand. Remember the continuity of surface fuels there. We just don't have it. We have the litter piece, but we do not have the woody piece. So very low duff load, pretty low surface fuel load, probably bordering on very low. Now let's take a look at the ladder fuels. As we look through here, we can see quite a ways into this forest, right? Which tells me there's not a lot of ladder fuels. We see some low-hanging branches maybe stuck on some of these, but branches that are dead, right? Not a lot of foliage around. So generally very low ladder fuels, but not quite as low perhaps as the mechanical or mechanical plus fire, because those were associated with the removal or the mastication. So it took us 3 fires to get here, but we're at a pretty low ladder fuel hazard here. Now, as we look all the way up to the canopy here, we definitely have more canopy fuels than the 2 mechanical units, but still nothing near what we had at the control site, where you basically had 70% or so cover and a lot of interlocking tree crowns. Here, we certainly have some groups of interlocking tree crowns, but there's also openings in the canopy too, where there's no tree crowns. So I would say we're pretty low on the ladder fuel hazard, moderately low on the canopy hazard, and as a result, overall we're talking about a pretty low wildfire hazard condition in this forest. Well, the forest health story is a little bit more complicated on this site. So we have the fires themselves that cause injuries to the trees, but nowhere near the amount of injury that we saw on the mechanical plus fire, and that's really the difference in residence time. There was a much higher residence time of the fire on the trees in the mechanical plus fire, and not so much here. So a little bit less injury, but there were multiple fires here. We're talking about 3 fires, which has more potential to injure these trees. Now, that's counterbalanced by the fact that we killed trees with the fires. And as a result, we reduced some of the competition. So we almost saw no net effect here on tree vigor. We think that over time, as we keep putting fire on this site and we keep reducing density, then we may see a positive effect in vigor. But at least initially, we're not there yet. Now we should talk about carbon. Okay, remember forest carbon. We're interested in this idea of being able to pull carbon out of the atmosphere and sequester it in these trees. Fire is a tough one because fire obviously emits carbon, right? If we kill a tree, it will become a slow emitter of carbon as that tree decays, but we also emit carbon that's on the forest floor, right? All of the surface fuel, even some of the duff is holding on to carbon, and that's gone immediately. So that becomes a negative side on the ledger. But on the positive side, we've reduced the probability of more severe wildfire, which means that these trees are more likely to hang on to their carbon if they were to experience a wildfire that is. So it's an odd story to try to tell here. With the mechanical only, it was an easier story in that we were holding on to carbon into the trees. We sent carbon in the way of lumber products to be sequestered into homes. Here, we're holding on to carbon in the forest. We've put some up in the atmosphere, but what is staying here is actually more stable if we compare that to the control.
So this is a treatment type that's really important to us here at Blodgett that we make sure to implement, but it might not be the most appropriate or feasible for all private landowners. So with a treatment like this, there's obviously some really great benefits in terms of fire hazard reduction and things like that. But along with those benefits come certain costs and risks to the landowner. So in a treatment like this, the landowner is holding all the liability for the burn. And as we talked about, you need kind of the right perfect conditions in order to do this type of a first entry burn with no pre-treatment. And a lot of times that's hard for a landowner to get. In addition, you have to deal with negotiating and getting permits, dealing with weather constraints. You're also on the hook for all of the costs. So finding crews that can actually implement the work. And this treatment, unlike some of our other ones, doesn't have a revenue generating component to it. So while it's important and we employ it here at Blodgett, it might not be appropriate for all landowners out there.